So let us start with a very simple question. How perpendicular component of polarization is equals to surface charge density? This question has come to our mind very often when we do derivations of Lorentz field or electric internal field or local field in dielectric polarization, and in even many other instances where we use this. In many of the books and videos, directly it is written perpendicular component of polarization equals to surface charge density. Why so, right? So let us first recall what is surface charge density, which is usually used with symbol sigma. Surface charge density is nothing but net charge on that surface by the surface area, okay? By that surface area. So this we all know. What is polarization? We're not talking about light polarization here. We are talking about electronic polarization, and electronic polarization is defined by separation of positive and negative charges, right? Separation of positive and negative charges again is how to quantify it, which is definition. Quantification is dipole moment per unit volume. What is a dipole moment? Dipole moment basically means separation of charges by certain distance. Okay, they should have some separation between the charges. The dipole moment, you use symbol mostly mu, it is equals to magnitude of charge multiplied by the separation. Let us say L. This is magnitude of charge. L is the separation between the charge. Right? So there is no separation, there is no dipole moment. And also the separation is huge, that there is no uh, influence on one another. That is also not a dipole moment. Okay. Now, how come the surface charge density equals to polarization? That too, not any component of polarization. It has to be perpendicular component of polarization. To find that, to conclude that, we have to consider one box along three dimension. The volume of the box is delta x, delta y, and delta z. That is, thickness along x direction is delta x. Uh, okay. Along y direction is delta y. Along z direction is delta z. So y direction according to here is left and right. X direction is front and back. So this direction is x direction, its thickness is delta x. Along z direction, its thickness is delta z. Z is up and down direction, right? So let us say we are applying an electric field only along y direction, that is from left to right. And we know electric field moves from positive side to negative side. If it is moving left to right, definitely left side should be positive, right side should be negative. Maybe we have connected some battery or something on the left side or right side of this one. Okay. So the left side is positive, right side is negative. So electric field is moving from left to right. Now what will happen inside the dielectrics? We are putting some value, Ey is not equals to 0, and we don't have any electric field alongside that direction. We don't have electric field along x direction, only along the y direction. Now, since we are applying electric field to this dielectric box, and in dielectrics are bad conductor of electricity, electrons will not electrons cannot be easily knocked out of the atoms. Electrons will still revolve around the nucleus, but their center of mass will be separated, the nucleus and electron. So one side will be positive, other side will be negative because of the influence of this applied electric field Ey. So Ey left side is positive, so left face will become relatively negative because opposite charges attracts. Right side of the face will become positive. So there is a separation of positive and negative charge of the dielectric. So this will create a dipole moment. So obviously dipole moment is will charge along this y direction on y direction faces, say right face or left face, multiplied by the separation. Now between what is the separation between left face and right face? Delta y. So this is dipole moment. So what is polarization? Dipole moment by volume. What is the volume? Delta x, delta y, delta z. Y component will cancel. So we have dy by delta x into delta z. So you can see that py is in which direction? Along the same direction as ey. Py is perpendicular to whom? Perpendicular to this right side face as well as left side face. What is the area of this right side face? You see it has height and it has length along x direction. So this area must be delta y into, no, sorry, delta x into delta z. This is delta x. So this is delta x. One side is delta x, other side is delta z. Delta x into delta z. So By is perpendicular to this delta x into delta z area. So it shows By is perpendicular to which area? Delta x into delta z area. So for this area, if you want to find surface charge density is equals to polarization, perpendicular component of polarization on this area. Similarly, if Ex is not equals to 0, x is in which direction? Front and back. Then we will have electric field along say x direction. Back side is positive, front side is negative. Back face will have negative charges, opposite charge again. Front side face will have positive charges. Again, Q x, suppose the separation is along x direction, delta x, volume is again delta x, delta y, delta z. So obviously x component will cancel out and qx will be equal, no, px will be equals to qx by delta y into delta z. Now px is in which direction? Similar to this ex direction, it is coming front and which is perpendicular to front face and back face. So front face and back face, whatever charge density is, surface charge density is, that is equals to polarization along y direction. Similarly, you find what will be the polarization component in terms of surface charge density along z direction, Pz. So consider it to be a homework. I think we have answered our question, how perpendicular component of polarization equals to surface charge density. Whichever area you want to find surface charge density, on that area, whoever is the perpendicular component of polarization, that is to find, or vice versa.